Yes, hello students, welcome back to our channel. So in our previous video we have got the information regarding the ionic radius and two types of ions, that is cation and anion. So in this video we are going to talk about the next physical property, that is ionization enthalpy. Ionization enthalpy is also known as ionization energy, both are same. Ionization energy. So we know that how an atom will be converted or how an atom becomes an ion. So when an atom either loses an electron or when an atom gains an electron, it will become an ion. Okay. So here, if you understand this word ionization enthalpy, this is the minimum energy required to remove the outermost electron from the neutral atom. Is known as ionization enthalpy. Yeah? So for example, we have this is the basic structure of an atom. We have nucleus and we have the shells, and we will be having the electrons over here. Okay, electrons 1, 2, 3, 4, 5, 6, 7 and 8. Okay, so we know that this is the outermost shell, or we call it as the valence shell. So if we have to remove this electron, that is the outermost electron, we know that there is some force of attraction between the nucleus and that of the positively charged nucleus and that of the negatively charged electron, that we call it as effective nuclear charge. Okay, so what happens? In order to remove this electron, negatively charged electron, what we have to do is we need to apply some energy from external energy. We have to apply some external energy, and that external energy is used to pull back, is used to overcome the force of attraction between the nucleus and the outermost electron, and it is able to get that electron out from the atom. Okay, so this process is known as ionization. Okay, so this is how an atom will lose an electron and it will get the positive charge. Okay, so that minimum energy which is required, to remove the outermost electron from the neutral atom is called ionization enthalpy or ionization energy. So now we have one more, second ionization energy and third ionization energy. Now let us look at that. See, the minimum energy which is required to remove the first electron we call it as ionization enthalpy. Now let us assume that an atom has lost an electron. That means it has become the monopositive ion. So now if we have to remove the second electron, the ionization enthalpy will be high. Okay, the energy which is required to remove an electron, from the monopositive ion is known as second ionization enthalpy. See, generally second ionization enthalpy will be more than that of the ionization enthalpy or first ionization enthalpy. Why it is so? It is because as the electron is lost here, this is a monopositive ion. Monopositive ion means the ion which has lost an electron, it has gained a positive charge, it is a monopositive ion. So it requires some extra amount of energy in order to grab the electron, the next electron from the monopositive ion, because the effective nuclear charge between the nucleus and the outermost electron in this case will be very high. So in order to overcome that high effective nuclear charge, we have to put extra external energy, that is the form of ionization enthalpy or ionization energy. So second ionization enthalpy will be higher than that of the first ionization enthalpy. Now let us look at the next one. So we have, after removing an electron from monopositive ion, it becomes a dipositive ion. That means 2 plus, Mg2 plus. Okay. That's an example. Okay, so that means that particular atom has lost 2 electrons. Now if at all we have to remove the third electron, the energy which is required to remove an electron, the energy which is required to remove an electron from the dipositive ion, is known as third ionization enthalpy. Okay, so generally students, third ionization enthalpy will be higher than that of the second ionization enthalpy, and second ionization enthalpy will be higher than that of the first, that means the normal ionization enthalpy. So this is the concept of ionization enthalpy. Ionization enthalpy or ionization energy is the minimum energy that is required to remove an outermost electron from the neutral gaseous atom. So now let us look at the trends along the periodic table. Yes, this variation of ionization enthalpy is dependent on the atomic size. So we know that down the group, as we move from top to bottom down the group, what happens to atomic size? Atomic size increases. Whereas along the period, what happens? Atomic size decreases due to the effective nuclear charge. The electron cloud gets shrinks towards the nucleus and the atomic size decreases. Now let us understand the concept. Let us understand the relationship between atomic radius and that of the ionization enthalpy. That is variation of IE, that is ionization enthalpy, down the group. So as we go down the group, atomic size increases. Okay, but as we go down the group, ionization enthalpy decreases. We require less energy to remove an outermost electron. Why it is so? It is because, let us understand the same concept. We have this basic structure of an atom. See, as we go down the group in the periodic table, we know that atomic size increases. Atomic size increases means the number of shells increases. Okay, then if the number of shells increases, the force of attraction between the nucleus and the outermost electron will be less. See, it is very obvious. The force of attraction between the nucleus and the first shell will be high because it is very near, and it decreases for the second shell, and it will be least for the next shell. So as the force of attraction between the nucleus and the outermost electron in the bigger size of the atom is less, nucleus will be having lesser hold for the outermost electron. If that effective nuclear charge is less, then it is easy to remove the outermost electron from the outermost shell. Okay, so as we go down the group, as atomic size increases, the ionization enthalpy decreases. So as we go down the group, ionization enthalpy decreases because as atomic size increases, the effective nuclear charge decreases. Okay, so let's take the example for this in order to understand this. We have lithium. It's ionized. This generally ionization enthalpy is expressed in kilojoules per mole. Let me write it. ionization enthalpy, it is expressed in kilojoules per mole. Okay, so let's have this lithium ionization enthalpy, it is 520 kilojoules per mole, and we have sodium 496, Na 496 kilojoules per mole. See, and potassium 419 kilojoules per mole, and we have rubidium 403 kilojoules per mole. See, observe this trend. This is the elements and their ionization enthalpies. As we go down the row, 520, 496, 419 and 403, the ionization enthalpies are getting decreased. Why they are getting decreased? It is due to, as we go down the group, atomic size increases, so the effective nuclear charge decreases. As the effective nuclear charge decreases, the force of attraction between the nucleus and the outermost electron is less, so it is very easy to take the electron out very easily. Now let us look at the variation of ionization energy along the period. So what happens to atomic radius? See, quite opposite atomic radius and ionization enthalpy variations. Okay. So what happens to atomic size? Atomic size along the period it decreases. Why? Because there will be no addition of new shells. As the atomic number increases, the number of electrons increases along the period, but there will be no addition of new shells. So what happens? The effective nuclear charge between the nucleus and the outermost electron increases in that case. So nucleus will pull the electron towards itself, so the electron cloud will shrink inside. So the atomic size decreases. So here, along a period, the ionization enthalpy it increases. We need more energy to remove the electron from an isolated gaseous atom. Along a period, the ionization enthalpy increases. Why? Because the atomic size decreases. So effective nuclear charge increases, so we require more energy to remove an electron from the outermost shell. So now let's take an example for this. Along the period, we have lithium. Its ionization enthalpy is, this is the elements we have, and these are the ionization enthalpies which are expressed in kilojoules per mole. Okay, so lithium it is 520 kilojoules per mole, and we have beryllium, it is 599, sorry, it is 899, and we have boron, it is 801, boron it is 801, carbon 1086, nitrogen we have 1402, and we have oxygen 1314, and we have fluoride, it is 2000 plus. It is exactly 2081. Okay, so these are the values of the ionization enthalpy along the period. See, observe here. So I have said you that along the period the ionization energy increase. It should increase, but there is some variations. We have lithium 520 and beryllium we have 899. That's an increase, but again it has decreased here. Boron and carbon it is increased. Nitrogen it is increased, whereas oxygen is less, and finally we have fluorine it is the high increase. So we have question mark on these two things. Why there is a gradual high increase in this beryllium and nitrogen other than that of boron and oxygen? It is because beryllium, if you observe the electronic conflict, we know that we call noble gases as the most stable elements. Why do we call noble gases the most stable elements? Because of their stable octet configuration are completely stable, completely filled orbitals. For example, s orbital maximum number of electrons that can be accommodated is 2 electrons. So in case of noble gases, if they have 2 electrons have been accommodated in s orbital. In case of p orbital, maximum number of electrons that can be accommodated is 6. And in case of noble gases, 6 electrons will be accommodated. So it means that the concept is, if the orbitals are completely filled, they are termed as stable. They are termed as the stable orbitals. So in the same case, observe here, we have beryllium. Beryllium, we require high ionization energy. It is because beryllium has completely filled s orbital. Because of this reason, it is more stable. So as it is more stable, we require extra energy to remove the electron. So now we have nitrogen. So in this case, nitrogen, we have half filled 2p orbitals. So we know that we have one more factor also. Half filled, completely filled, no doubt, completely filled orbitals are highly stable. For example, p orbital 6 electrons, d orbital 10 electrons, they are highly stable. So in case if they have at least half filled orbitals, they are also considered as stable itself. For example, if we have 3 electrons in the p orbital and if we have 5 electrons in the d orbital, they are also termed as the stable element itself. See, in this case, in nitrogen, we have half filled p orbital, so that we consider it as a stable thing. So because of this reason, we have a high increase in the ionization enthalpy. And you know that fluorine, it's also having higher ionization enthalpy. See, the trend goes like this: ionization enthalpy increases. Yeah, so this is regarding the ionization enthalpy, students. Thank you.